Let us understand splitting of d orbitals in octahedral complexes. Octahedral complexes means how many ligands are there? What is the coordination number of central metal ion? 6. How the ligands are going to approach? We are assuming ligands are approaching along axis. What's our imagination? X-axis to our left, right. Towards you and towards me, y-axis. Up and down is a z-axis. So ligands are approaching along axis. Metal ion is at center. Which orbitals are there on metal ion? 5 orbitals are there. 5 d orbitals are there. Which are those? dxy, dyz, dxz, dx square minus y square, dz square. Let us understand their nature. dxy orbital, lobes are between x and y axis. dyz orbital, lobes are between y and z axis. dxz orbital, lobes are between x and z axis. So these orbitals are axial or non-axial? Of course non-axial. How many these orbitals are there? 3. Keep this number in mind. Now other two orbitals, dx square minus y square, lobes are along x and y axis. Last, dz square orbital, lobes are along z axis. And one ring is there, donut shape is there. I said it's like medvada. And that ring is in which plane? XY plane. So x and y axis components are there. I can divide these 5 orbitals in 2 parts. 3 are non-axial and 2 are axial. So now 2 teams are there out of the 5. One team has 3 players, dxy, dyz, dxz. Other team has 2 players, dx square minus y square and dz square. As ligands approaches along axis, then they will strongly interact, they will strongly repel. Which orbitals? Axial orbitals. Which are axial orbitals? dx square minus y square and dz square. Because of repulsion, what will happen? Energy will increase or decrease? Energy will increase more. Here we are talking about repulsion. So relative to energy of free metal ion, d orbitals of free metal ion, energies of these orbitals, whichever I am talking about, the splitted orbitals, will be always higher because of repulsion. But among repulsion I am talking about where is more repulsion and relatively less repulsion, because to have relativity we are with hypothetical consideration. What are we considering? We are considering spherically symmetrical hypothetical field around metal ion. Spherical symmetrical negative ligand field remains, due to which what happens? Degeneracy of those all 5 d orbitals will be retained, will be preserved, will be kept as it is, will be undisturbed. But spherically symmetric field is hypothetical. It is not the reality. Reality is octahedral. Now in our consideration, octahedral means 6 ligands are there. 6 ligands are approaching along the x-axis, y-axis, z-axis means along axis. So if they are approaching along axis, then few orbitals will experience more repulsion, relatively less repulsion other orbitals will experience. But anyhow, we want equilibrium. We want center of gravity. We want barycenter energy. We want equilibrium energy. Then how can it be possible? If one set increases, other set has to decrease. Means it is if how while doing a drill as such, it looks good. By the way, in order to have proper balance as such, when we stretch the one hand, by the same time the other hand goes back. It's a way of balancing. Just to observe sports player, there also you will find the balancing out. Equilibrium is a very important in our life also, in behaviorology also, and in chemistry also. To maintain that equilibrium, energy of other set will decrease. What is other set? dxy, dyz, dxz. Let me label those sets now. 2 orbitals, dx square minus y square and dz square. These 2 orbitals means a doublet. In group theory, the doublet is represented by symbol small e. And 3 orbitals, dxy, dyj, dxz, it is a triplet. So triplet is to represent by symbol small t. These are axial orbitals. So only simply we are representing as E or we are representing as 1. These are non-axial orbitals who dxy, dyj and dxz. For that we are using number 2. So T2, 2 means non-axial. Then whatever the geometry we are considering, it is octahedral. What do you think? Octahedral geometry has center of inversion? Yes, center of inversion remains. And center of inversion we represent as the term small g. Gerade. Geradness means existence of center of inversion. It is there for the complex. So let it be the T2 orbital or E orbital. Let it be the triplet set. Let it be doublet set. We have to represent it. So representation is T2G and EG. Now again come to the energy level. Since EG orbitals are axial, they will experience more interaction, more repulsion. So their energy will decrease. And T2G orbitals relatively experience less repulsion. Therefore, their energy will decrease. Now we have to answer how much increase and how much decrease. Let me consider this gap between T2G, that's the lowest splitted orbital, and EG, highest splitted orbital, is delta O. If that complete gap is delta O, how much distance, how much lowering of energy is there for T2G and how much increase in energy is there for EG? So decrease in energy, so minus sign will be there for energy, and here relatively plus sign because equilibrium we are considering as 0 and complete gap is delta O. How to find that? I give hint to you. Let us consider here 3 orbitals, means 3 kids are there. All are of the same age, same weight they do have. And upside 2 kids are there. They also are of the same age, same weight is there. Means it is like a seesaw in the garden. One side 2 boys are there of the same weight. Other side 3 boys are there of the same weight. Time being distance between their sitting arrangement do not count. They are sitting at one place. So one side 3 are there. Other side 2 are there. What do you think? From central position, from equilibrium position, now we can say barycenter or we can say center of gravity, central aspect, or from fulcrum, 2 boys and 3 boys. Who should be near to the fulcrum? Who should be near to the center? These 2 boys or 3 boys, so that there should be equilibrium, so that seesaw will be horizontal, parallel to the ground. Yes, what do you think? These 3 should be near. Yes, 3 should be near and 2 should be away. Means relatively I am talking about. How much near they should be or how much away these 2 boys should be, that we have to find out. Total 5 kids are there. So every kid has a weightage, say consider out of 1 will be 0.2, 0.2, 0.2. So total 0.2, 0.2, 0.2, here 0.6 will be there. Here weightage will be what? 0.4. Weightage is weightage I am talking about, weight point of view. So weight is less, therefore distance is more. Here weight is more, so distance should be less. Total distance is 1. Well, total multiplication should be same. Let me consider distance as x. So 0.6 into x. Here 0.4 into y. Both should be equal. When it's possible? When this distance becomes, distance of these 3 boys is 0.4 of complete distance, 0.4 delta O, and this distance equal to weight of others, 0.6, and total distance delta O, 0.6 delta O, 0.4 and 0.6, if you sum up, answer is 1, that is delta O. Means what I wanted to say, those 3 boys will be separated by distance 0.4 delta O, means 0.4 unit, and these 2 will be separated by 0.6. So in splitting diagram, where 2 boys are there, where 2 orbitals are there, EG set is there, that will increase by amount 0.6 delta O, and where 3 boys are there, 3 orbitals are there, it will decrease by amount 0.4 delta O. Total gap is delta O. This is the understanding of splitting diagram of octahedral complex. Other way, we consider this complete gap as 10 dq. dq is a parameter or unit for measurement of the energy. Complete gap is 10 dq. Then the gap of barycenter and highest speed orbital will be 6 dq. The lowest orbital and barycenter will be 4 dq. So what is the energy I can consider? 0.4 delta O or minus 4 dq. Energy of EG plus 0.6 delta O or plus 6 dq. Total gap delta O or 10 dq. It is about the splitting diagram. Now understand this energy. What is in true sense? We consider free metal ion. No any kind of interaction. All d orbitals will be of same energy level. 5 d orbitals are there. Then hypothetical consideration. Hypothetical spherical field we are considering. So energy levels of all 5 d orbitals will increase because of repulsion. But it is not the reality. Reality is octahedral. Therefore splitting diagram we are finding. So whatever the splitted orbitals are there, they should be of higher in energy than free metal ion orbitals. That's a crystal field theory basis. You can prepare description with the help of these 5 points. First point is a basis of CFT, which involves metal ion as a positively charged and ligand we consider as a negative point charges, and they impart a negative field on the d orbitals, electrons present in d orbitals of the metal ion, and spherically symmetric hypothetical field and how the energy changes occurs. That's a general idea as a basis of CFT you need to explain. Second point is the shapes of d orbitals, because splitting depends upon orientation of these d orbitals, directions of the lobes of d orbitals, and ligand approach. So if shapes are clear, then only you can describe the splitting. And third point, how exactly is a ligand up with relation to the shapes of d orbitals, that we need to describe with the help of diagram. The fourth point, in the real sense, how splitting occurs, the splitting gap, the labeling of energy terms, labeling of those orbitals, spherically symmetrical hypothetical field, energy of the free metal ion, complete splitting diagram with labeling. Fifth point, explanation you can give, comment you can give about the splitting, that's a splitting parameter. Here I like to discuss from second point. It's a representation of all 5d orbitals. First one, d z square orbital, where lobes are along z axis and donut shape of ring is there in xy plane. Second is dx square minus y square orbital, where lobes are perfectly along x and y axes. So these two orbitals, dz square and dx square minus y square, are axial orbitals. It is a doublet. Therefore, it is represented by symbol small e. Because of center of symmetry, we can represent them as Eg. If a resultant complex has the center of inversion, then we will represent by Eg. Otherwise, simply we will say as E. Especially for tetrahedral complexes, we represent it by E, and for octahedral, we represent it by Eg. Third orbital is dyz, where lobes are in between y and z axes, perfectly in between y and z axes. Fourth one, dxz orbital, where lobes are between x and z orbitals. And last one, dxy orbital. Here also lobes are between x and y. Only from this representation you will understand all these three comes in one category. Lobes are not along axis. Those are represented by the symbol T2, T for triplet, 2 for non-axiality, and G for gyroidness. In case if complex has that centrosymmetric arrangement, then we will use the term T2G. So this diagram describes two sets of orbitals at metal ion, Eg and T2G. Here is a diagram representing approach of 6 ligands and the shapes or orientations of orbitals present at central metal ion. How cluster of orbitals is there. Interestingly, see there. Ligands are approaching along axes. 6 directions are there. Ligands are represented by black ball. And the orbitals which are axial, those are pointing towards center of the face of the cube, are represented by gray color. And the orbitals which are non-axial means T2G sets, their lobes are represented by a white color. If you observe them neatly, those are pointing towards center of each edge of a cube. T2G set encompasses three orbitals dxy, dyz and dxz. EG set encompasses two orbitals which are shown by gray color or are shaded. Those orbitals are dz square and dx square minus y square. And a common conclusion for octahedral complexes, EG orbitals are directly facing towards the ligand, therefore they experience more repulsion. Therefore, relatively their energy should rise is our expectation. Now let us see actually how splitting is there in the d orbitals in octahedral field. This diagram is very important. Actually, it is the essence of our discussion. See, left side one energy arrow is represented. As we go high, as we go up, energy of the respective orbital or orbitals will increase. The left side, free metal ion. How many orbitals are there? 5. Which are those? dxy, dyj, dxj, dz square and dx square minus y square. And crystal field theory assumes hypothetical, spherical, symmetric field. In presence of that spherically symmetric hypothetical field, that's a ligand field. See upside, a diagram is shown there. Metal ion is at center and negative spherical field is represented. So each orbital will experience same kind of repulsion. There's a no favorism, there's a no victimization. All orbitals will raise in equal amount of energy. So elevation of energy of all 5 orbitals is represented. And later on, the reality what it is represented by upper right diagram where ligands are approaching along axis. Negative sign is there for the ligand approach and metal ion is with positive charge. And field here we are considering is octahedral. That results change in the energy levels of the orbitals. Energy levels of sets of orbitals. Two sets are there. One is T2G, other is EG. See below barycenter by distance zero point 0.4 delta O for octahedral. The dxy, dyj, dxj, the triplet is there represented by T2G. And upside the doublet is there. dz square and dx square minus y square orbital. It is represented by Eg and is elevated by amount 0.6 delta O. Other way, it can be said as 6 dq increase of Eg orbitals and 4 dq is a decrease of T2G orbitals. If we consider that complete energy gap as a 10 dq, what is that complete energy gap? The energy gap between T2G, that's the lowest splitted orbital, and highest split orbital Eg is called crystal splitting parameter. And that crystal splitting parameter is represented by symbol delta O in case of octahedral field or 10 dq. And at center there is a barycenter. One line is there. A faint line is there. Now energy C, energy of T2G set is minus zero point 0.4 delta O or minus 4 dq with respect to barycenter, with respect to equilibrium energy level. Energy for EG set is plus zero point 0.6 delta O or plus 6 dq. Now important point. Pay attention towards energy level of free metal ion d orbitals. Compare their energy with metal ion d orbitals in spherically symmetrical field. What are you finding? There is a rise in energy. What does it indicate? There is a repulsion between metal ion d orbitals and a negative spherical field. What is the situation in octahedral? In octahedral field, also there is a rise in energy of any orbital with respect to energy of free metal ion d orbital. What does it mean? Each orbital experiences repulsion. that I was saying in the previous video. Energy of splitted orbitals should be higher than the energy of free metal ion d orbitals. Now the concept might be the very clear to you. While drawing, take care that the energy of splitted orbitals will be higher than the energy of free metal ion. One important correction I suggest here: Eg orbital energy level should be higher in rise compared to decrease in energy level of T2G orbital, because zero point 0.4 delta is a decrease of T2G and zero point 0.6 delta is an increase of Eg orbital. 0.6 higher than 0.4. So you should represent the diagram in such a way that Eg orbital will be higher in energy compared to the shown here. I hope you are getting this point. We studied the splitting and we found the crystal field splitting parameter delta O or 10 dq. I want from you some descriptive answer. You have to define that delta O or 10 dq. What is that actually? It's the energy gap between splitted orbitals. Lowest splitted orbital, that's a T2G, and highest split orbital, that is EG. Just you define there in the comment box. Is the splitting diagram for the octahedral complexes clear? If the ligands are stronger, more splitting will be there. If ligands are weak, then less splitting will be there. When we study electronic configuration, at that time this concept will be the more clear. So let us discuss next time other geometry for complexes and its splitting.